Okay, so we're going to look at now what happens if some of your zeros are complex. What if you take your polynomial, you set it equal to 0, and one of the factors gives you solutions that are complex numbers, imaginary numbers. So our goal is that we want to be able to write any polynomial in completely factored form. So we were doing this in the last lecture, taking our polynomials, write them in completely factored form. It's just that I rigged all those examples so it would be possible. Okay, so now we're going to look at some examples that throws up a little roadblock. So completely factored form means I want all my factors to look like x minus something, and those somethings are the zeros, or the x-intercepts. So let's say I want to do this for p of x equals x squared plus 1. I want to write this in completely factored form. So that means if I want to know its factors, I'm going to try to find its zeros. So I set x squared plus 1 equal to 0. Get x squared equals -1. I square root both sides, and x equals plus or minus the square root of -1. Now this is a problem, right? Up until this moment in the class, we have said no solutions, right? This doesn't mean anything. Now, we're going to change our tune. This is now going to mean something. So we can't see it. It's not on the real number line. You don't graph it, but it does exist. Okay, so we're going to say, we're going to just pick something. We're going to say, let I be the number that when you square it, you get -1. Right? So I'm trying to solve this equation, x squared equals -1. We're just going to say that there is such a number, that when you square it, you get -1. There is no real number because any number when you square it is going to come out positive. If it's negative, then you have negative times a negative, which is positive, and it's positive, it's going to be positive times positive, which is positive. So there is no real number. There is no number in the system of numbers that we have always lived in so far, but we're going to make one up. We're going to say x equals the number I. I is the square root of -1. I is the number that when you square it, you get -1. Okay, so I'm going to have two zeros, x equals plus or minus I. Now I know it's hard to wrap your head around just inventing a number to suit our needs, but that's what we've done with all numbers. Okay, go back to how you first started learning math in elementary school. Even before elementary school, you learned to count, right? And you knew that there were numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? And then you learned that there were numbers even bigger than that, right? That you could make bigger and bigger numbers. Your universe of numbers just keeps expanding. And then you learn there's a special number called 0, which means nothing, right? And that's a new thing developmentally. When you teach children about math, you don't tell them about 0 for a while. So then you start thinking like, oh, I can count to any number in the world. I can count to 0. I can count to 1 billion. And then somebody tells you that there are numbers between the numbers, right? We make up a new kind of number called a fraction or a decimal. And that like blows your mind all over again. There are these other new numbers, right? And then somebody tells you that there are numbers between those numbers that you can't write as a fraction, like pi, like the square root of 5, right? Those numbers are irrational numbers. And those, historically, each of these events that we teach children, daily, regularly, was a mind-blowing event in history when 0 was invented, when fractions were invented, when irrational numbers were invented or discovered, right? They're really big events. And complex numbers are like just another one. So it seems like, what? You're just making up a number out of nowhere? That's what all numbers are. All numbers are just invented to suit our needs. So we had the need of a number that when you square it, you got -1, so we invented it. So the reason I wanted that is because I wanted to be able to write x squared plus 1 in completely factored form. So its zeros are plus or minus I, which means I can write x squared plus 1 as x minus, right? And then I just put in the zeros, I and -I. So now I've written it in completely factored form. So the letter I is the symbol we use to denote the square root of a negative, square root of -1. So if k is a positive real number, then I can write square root -k. I would simplify to be written as the square root of -1 times k, which is the square root of -1 times the square root of k. And the square root of -1 we rewrite as I. So this is I times the square root of k. So any time you want to take the square root of a negative, you just take the square root of the positive number and throw an I next to it. For example, square root of -49. I would rewrite this as the square root of -1 times positive 49, which is the square root of -1 times the square root of 49. Square root of -1 is I, and the square root of 49 is 7. So this comes out to 7I. The square root of -8, I would rewrite as the square root of -1 times 8, which is the square root of -1 times the square root of 8, which is I times the square root of 8. Yeah, you could simplify square root 8 by rewriting 8 as 4 times 2. And then that's I times the square root of 4 times the square root of 2. And then you can take the square root of 4. So this would be 2I square root 2. Sometimes it's handy to be able to simplify a radical like that. It's sort of not the focus of the class, but it is something you should be able to do. Okay, and then this last one, I squared. Well, I is the square root of -1. What happens when you take a square root and square it? They cancel, so this becomes -1. So a complex number is a number of the form a plus bi, where a and b are real numbers, like 2 plus 5i, and it has an imaginary part, which would be the 5, and a real part, which would be the 2. So up until now, we've just been looking at strictly imaginary numbers. And now we can combine them with real numbers, and these are called complex numbers. So is the number 3 a complex number? Why not? So a complex number just means I can write it as a plus bi. Can I write 3 as something plus something times I? Yep. So it is complex. So regular old real numbers are a subset of the complex numbers. The imaginary part is just 0. Okay. And an imaginary number is a number of the form a plus bi, where a is 0. So your paper says it correctly. Mine had a little typo. Okay. So it's just a number that looks like bi. Strictly imaginary number. So we can do arithmetic with complex numbers. You do it exactly the same way as you do arithmetic on a variable, right? Treat that I like a variable, like an x or an n. And the only thing you have to remember is that I squared equals -1. This example, I took it out of your packet, right? Yeah. 2 plus 3 root 7 0? Oh, okay. Okay. So if I wanted to add 2 plus 3 root 7 plus 1 plus 5 root 7, everything in there is addition, so I can just drop the parentheses and combine like terms, right? Those guys can be combined, and those guys can be combined. So I get 2 plus 1 is 3, and 3 root 7s plus 5 root 7s is 8 root 7s. Okay. So you treat i's the same way you would treat radicals or variables. So if I want to add 2 plus 3i plus 1 plus 5i, combine the like terms. The 2 and the 1 makes 3. The 3i and the 5i makes 8i. Same with subtraction. Just have to remember to distribute the negative. So this says 2 plus 3i minus 1 minus 5i. Distribute the negative, and then you combine like terms. So 2 minus 1 is 1. 3i minus 5i is minus 2i. And then to multiply them, you FOIL, just like you would if that said 2 plus 3x and 1 plus 5x. Just FOIL. So you have 2 times 1 is 2. It's first. Outer is 2 times 5i, which is 10i. Inner 3i times 1 is 3i. And 3i times 5i is 15i squared. Now I just have to remember that I squared is really -1. So this says 2 plus 13i minus 15. So I have -13 plus 13i. Okay, you do E. Multiply 2 plus 3i times 2 minus 3i. Okay, so we FOIL it. We get 4 minus 6i plus 6i minus 9i squared. Okay, so that's nice. My minus 6i and my plus 6i cancel. And then I have 4 minus 9, and instead of I squared, I'm going to replace it with a -1. I squared is -1. So this says 4 minus -9, which is 4 plus 9, which is 13. So something special happened there. I multiplied 2 complex numbers with i's in it, and I came out with a strictly real number, 13, plain old 13. So we multiplied 2 complex numbers and we got a real number, no imaginary part. So that happened because 2 plus 3i and 2 minus 3i are what we call conjugates of each other. Okay, so the conjugate of the number a plus bi is a minus bi and vice versa. A plus bi and a minus bi are conjugates. So the conjugate of 2 plus 3i is 2 minus 3i. And we put a bar over a number to denote its conjugate, but we don't use that notation very much, so don't worry about it. Okay, so it's going to be helpful to have a shortcut for multiplying two conjugates together. So I want to multiply a plus bi times a minus bi. I'm just going to FOIL it out. I'm going to have a squared minus abi plus abi minus b squared I squared. Just did FOIL. My abi terms cancel, so that's nice. And I get a squared minus b squared times -1. Replace my I squared with a -1. And so I end up with a squared minus -b squared, which is a squared plus b squared. Because I've got the minus and the negative. Makes a plus. So the first place where we find conjugates helpful is when we're dividing complex numbers. So if we want to do 2 plus 5i divided by 2 plus I, and I want to write that in my standard form, a plus bi, the trick I use is the conjugate. Multiply the top and bottom of the fraction by the conjugate of the denominator. So I can multiply the top and the bottom by 2 minus I, and it's legal because I'm really multiplying by a fancy form of 1. 2 minus I over 2 minus I is just 1. And the reason it helps is because it's going to make my denominator a strictly real number. It's going to get rid of all the i's in the denominator. So I FOIL the numerator, and I get 4 minus 2i plus 10i minus 5i squared. And I can FOIL the denominator, or I can use my shortcut a squared plus b squared. But let's FOIL it just for now so to get into the habit. 4 minus 2i plus 2i minus I squared. All right, so now I simplify. This is my like terms are my 4 and my plus 5, right? Because I squared is really -1. So instead of subtracting 5i squared, that's the same thing as plus 5. The I squared changes the sign. So I have 4 plus 5 is 9. -2i plus 10i is 8i. And then in my denominator, my like terms, I've got the 4 and minus I squared, but I squared is really -1, so this is really plus 1. And the 2 i's cancel. So this is 4 plus 1, which is 5. And the last thing I'm going to do is break this fraction into two fractions. I can divide the 5 into both pieces. 9/5 plus 8/5 I. That way it looks like a plus bi, right? The definition of a complex number. All right, I think that's a good place to stop.